Now we want to look at another class of equations where we can generate solutions implicitly by somewhat direct integration kinds of methods, and that is what's called an exact equation. So to get into this, let's start with the calculus 3 problem. So assume I know that y is a function of x, and you know that x and y together satisfy this relation here. X squared y plus 4x to the y is 8. I want to differentiate this equation in x to find a differential equation for dy dx. This is kind of a calc 1 problem, actually it's an implicit differentiation problem, but we'll see how it ties into calc 3 stuff in a little bit. So I just want to differentiate this equation here. And so to do that, I just take d dx, apply it to the entire thing, and do product rule and chain rule on both sides. So for this first term, I have x squared y. So if the derivative hits the x squared term, I will get a 2x times a y. When the derivative hits the y, I will get x squared, and now times a dy dx, because when the derivative hits y, you get a dy dx. Then I have the next term, the 4x e to the y. When the derivative hits the 4x, I just get 4 times e to the y. When the derivative hits the e to the y term, I will get my full 4x e to the y, and then times a dy dx. And that equals 0 because the derivative of 8 is 0. I can now rearrange things a bit. I will see a 2xy plus a 4e to the y that terms without a dy dx, and then plus x squared plus 4x e to the y times dy dx equals 0. Or if I want to actually solve it for dy dx here, I can, to get me to dy dx equals a negative 2xy plus 4e to the y divided by x squared plus 4x e to the y. I'm going to box this one up here because this will be the more important equation for us to look at here. So that's just doing implicit differentiation, taking a derivative when you have x and y mixed together, but your y is a function of x. Now, a related question. Find a solution to the differential equation 2xy plus 4e to the y plus x squared plus 4x to the y dy dx equals 0. Condition y of 2 equals 0. Hang on a sec, that looks familiar. This is actually the exact same expression we had up here on the previous page. And our work in this problem here tells us that this expression here is exactly the derivative in x of x squared y plus 4x e to the y. That would hit equaling 0. So that means now we can sort of integrate both sides of this equation here to give us then, we have x squared y plus 4x e to the y equals some constant c. And I can find c from the initial condition by plugging in x being 2 and y being 0. This term will go away, and so I'm then left with 0 plus 4 times 2 times e to the 0 equals c, which means that c equals 8. So my solution here is x squared y plus 4x e to the y equals 8, which is the function we had started with for the first part of this problem. So the point of this idea is, if I have an expression where this expression on the left-hand side here is exactly the derivative in x of some function of x and y, then I can solve it this way. I can write it out in that form, integrate the whole expression, and then get to an answer by finding a value for the constant c. The point is, we've written our equation in this form, some function m of xy plus some function n of xy, dy dx equals 0, and we knew there was some function psi such that taking d dx of this function psi of x, y of x, gave us exactly the left-hand side there. So now is where calculus comes into play. What is this derivative here? If I'm considering the function psi of x, y by itself, and I want to look at the derivative in x of psi of x and then this function y of x in here. How do I find this derivative? Well, this is the multivariable calculus chain rule. Right, tree diagrams and stuff where you're multiplying different derivatives by each other. That's what this one is. This is the partial of psi with respect to x times 1, that's a dx dx in there, plus the partial of psi with respect to y times dy dx. Well, this format matches up really nicely with our expression up there. So what we need is that this function m is the derivative in x of this function psi, and this n is the derivative of psi with respect to y. And that leads us right to our definition of an exact equation. The differential equation, written in this form, m of xy plus n of xy dy dx equals 0, is said to be exact if there is a function psi of xy so that if I take the partial derivative in x, I get m, and if I take the partial derivative in y, I get n. And in this case, because the differential equation is d dx of psi, we know that solutions are given implicitly by psi of x, y equals some constant c for a c depending on the initial condition. Now, these types of equations do show up in other fields besides just your math classes. You will sometimes hear this psi referred to as a potential function, a stream function, or a conserved quantity. That last one usually relates to energy, right? If I have the total energy of a system that is conserved over as time goes on, then I can define the solutions this way because the energy will always be constant because that's what the energy is. So all of these show up in physics and engineering and a bunch of different places. You'll see things like this where you have these different terms, and really what you're talking about is the level curve of some function where the solution must live because the solution obeys some certain conservation law or some sort of property that means it will satisfy an equation like this.